Yes, so we're going to get to the second part of our lecture. We have an hour, I believe, from 2:30 to 3:30, and then we're going to start the workshop. I know some of you are having like mild environmental issues with your computers, and we expect that, so there's definitely going to be time when the workshop starts for us to like go around and, you know, if your shell isn't working or this or that, we'll do that today. What's going on, Kate? Is it?
I feel like
it's still.
thing that's echoing. I feel like.
Yeah. Is it?
Okay. It's echoing, but I thought maybe if I muted it.
We'll figure it out one day. Thanks, Kate. No, it's cool. Okay, yes, so continuing where we left off, we're still talking about encoding. So I know we rush through some of this stuff, but we're just trying to get a sense for how do you represent different things in terms of ones or zeros. And usually you're going to represent it at a higher level anyways, with like an object or a number or something that you're provided by the language. But yeah, here's a picture. I'm sure someone here knows more about art could tell me who this picture is. Who? Sarah. Who's he? She. Who's she? He. French pointillist. Well, it's very nice, but now that there are computers, we don't need artists because we can represent it all as ones and zeros. So I'll tell you first, we're going to watch that again because this is definitely the highest quality transition you will see the whole time. I didn't make it. I wouldn't spend this much time on a transition. Whoa! So yeah, it's all red, green, and blue pixels. So your screen is made of lots and lots of LCDs or LEDs, which are these tiny, what does an LED stand for? Light emitting diode. It's like the simplest thing that you can provide it electricity, and it's able to it has like 3 color channels that it can understand a value between 0 and 255, and 0 means none of that color, and 255 means a really bright, pure version of that color. And each one can have red, green, and blue at the same time. So if it has all of them, that's white. None of them, it's black. And obviously, there's all the colors in between. So yeah, we break it down into little boxes. And how might we think of this in terms of information? So we have what's sometimes referred to as a bitmap, which means that we have, oftentimes it's represented as 24 bits, RGB. So red, green, and blue, each one you get 8 bits, which gives you only so many values you can represent for each. I believe when it comes to colors on the web with CSS, it's actually represented in 32 bits, where it's red, green, and blue, but the last 8 bits are an alpha channel. So what that means is that it's like how see-through it is. So if the alpha channel is at 0, I think that means well, it has that color, but you can see right through it. So it might as well not exist. Whereas if it's at 255, that means it's a solid color like you would expect. But somewhere in the middle, if there was something behind it, you could see that something behind it, almost like it's translucent. Generally, though, we're not going to be, yeah, I hear the echo too, it's weird. Generally, we're not going to be thinking of colors in terms of bits, but this is what it actually is in memory. It might take up 32 bits total, and that represents our entire color. And an image is just a 2x2 array of all of these colors. So sound. This is a very interesting speaker that, I don't know, we're just showing you the speaker. So how do we encode sound? Well, sound is a wave, and the simplest way to do it is you have time, and at every time signature, however fast your, what do I want to say, your sample rate. So how often you're going to be sampling per second, maybe 60 times, maybe 100 times. I don't know what's actually considered good. 44,100 samples per second is a lot more than I would have guessed, but I guess there's a lot of information there. And while you can't represent a wave, what you can do is at each time increment represent the lowest thing that you could represent or the highest thing, and that produces something like a wave. So when audio is uncompressed, when you're representing audio directly, it's just one of these after another. And that represents a wave, but very often things are not represented this way. Instead, they're represented as something like an MP3, which is a type of compression. And the idea there is that it's too much to have one after another, like, 44,100 per second of these 16-bit or 32-bit numbers representing the amplitude. So someone found some kind of abstraction in which they could take all of this information, boil it down to some much smaller amount of data, and then later take that amount of data and unpack it to be this much larger thing. And that's true with all types of data. So like when I'm recording this movie, it's a MOV file. And what that is it's a pixel. It's like a 2D array of pixels, which are as big as my screen. And then it has 30 of those a second maybe. And it has however many of those are, if I'm speaking for an hour, that's however many seconds are in an hour. And that is massive. So like an uncompressed video is a few gigabytes right off the bat. And that's pretty hard to work with, which is why, when you put something on YouTube, things are compressed in some way. But compression is ultimately just some transformation in which you can make your thing a lot smaller, but then you can later retrieve what you need. And we're not going to work much with compression algorithms, but it's something to think about because it does every now and then come up on interview things, and you can think of it in simple ways where it's like, if I have, let's say I were to have something like, so some simple version of what compression might look like is if I have like AAA, BB, CCC, that takes up 1, 2, 3, 4, 5, 6, 7, 8, 9 characters. So that's 9 bytes minimum. And if I represented it like A4, B2, C3, well, that's actually the same information that I can unpack later, but it's only 1, 2, 3, 4, 5, 6. And that's all any compression algorithm ultimately is. It's just some way of transforming it into something that is ideally smaller. But you'll actually notice that there are times where you can compress something and it gets larger. Because sometimes this, so let's say I actually had just ABC. Sorry, something like ABC. Well, if I compress that with this algorithm of mine, I say A1, B1, C1, that's actually larger. And it's not a great compression algorithm for this. So compression algorithms are always based on the data that they're capturing and some aspect of what you want to do with that data. So like, I have no idea how Netflix actually does its encoding, but something important is that it's not encoding the whole movie at once. It's encoding it in these like tiny little snippets that it sends out one at a time. And I'm sure that makes it different from something where you assume you can have the whole video at once. Abstractions and languages. So we've talked a little bit about the hardware of a computer, but we haven't really talked about how you might represent your code. And we did speak about assembly, and this is what assembly is. So here's my assembly down here. And what I'm saying is I have this built-in operation in my computer called add. So processors generally can only do a handful of things. And it's basically arithmetic, Boolean logic, and moving things from one place to another. In terms of video game recommendations, there is this game called Shenzhen IO. I don't know if you've ever heard of it, but there is not a better way to learn electrical engineering as a video game. Like you have to write assembly in this made-up programming language. Obviously, if you're busy doing this course, it might be an extra intellectual burden you don't need. I remember I played a different game that guy made, Space Chem, when I was doing some CS research, and I used all my intellectual power on the game because it's that difficult, but it's a really good way to I don't know, it's fun. You get to experiment with circuits, and you see how just this very minimal amount of instructions. So modern processors follow what's called RISD, so reduced instruction set design or something. And what it means is that instead of having your processor be able to do 1,000 things like square root or something like that, instead it can only do a handful of things, but it can do each one of them really, really fast. So it might not have division, but it does have like addition and subtraction, and actually that's enough. That's all you need. You can do division as repeated subtraction or something along those lines. And there's this idea that ultimately it's better if a processor can only do a handful of things. So how might we read this? So we talked a little bit about registers, and registers are this idea that on the processor itself, it has this table where it can hold like 10 or 20 items or something. And it can't hold more than that at a time, so it has to interact with memory anytime it wants to replace one of these. But anytime you're doing an operation, you ultimately have to deal with these registers. So what this is saying here is I have this function add. I want you to read what is currently in T6, and think of this like a variable you would name. It's just you can't name these variables. They have names which always start with a $sign for some reason. There's usually a letter S or T that means something, and then a number which is how many of them you have. So this is saying grab what's in T6, grab what's in T1, send them to the part of your processor that knows how to add numbers together, and whatever comes out of there, store it in T2. What was that? I'm wrong? Okay, it's take the value in register 1, add it to the value in register 2, and store it in 6. Exactly. And the truth is, it's arbitrary what order it is. A different instruction set could mix these up. But the idea is that whoever made the processor just worked out the numbers to say, okay, I have only so many instructions, and I can represent it over here. So 1, 2, 3, 4, 5, 6. What's 2 to the power of 7? Not 128. So like this opcode says, okay, I can represent 126 possible different operations. In this case, 0 means arithmetic. And I guess there's more to it where there's this section and the number 32, or 100,000 in binary, represents addition. So something else would represent subtraction. And it's just how you're going from here to here, but it's really one-to-one. Like, if you were just flipping these switches on and off, your computer's going to read all of these at a time. I'm assuming this is 32. So 6 plus 5, 5, 5, 5 plus 6. So 12 plus 20 is 32, yeah. And when you see that a processor says it's 32-bit or 64-bit, what that means is what the size of a single instruction is. So your computer, it's made a regular number, so wherever your computer knows to look for the code and start like reading that code, it just goes 32 bits at a time and reads the 32 bits, and it's able to translate this to say, oh, you don't have to think of it in this way, but it reads this to say, okay, so they mean arithmetic. And they want to grab something from here, and they want to grab something from here, and they want to store it here, and this is some extra thing we're not using, and what we're doing is addition. And that's everything it needs to know for this instruction that it has. And right, we can represent it in different ways, but ultimately the computer's seeing it like this. And really, the computer doesn't see ones and zeros, it sees electrons being somewhere or not being somewhere, and that gets so low level that it's hard to think about. If you look online at these like YouTube videos of like Intel saying like, here's how we designed a processor, within a minute it will make no sense. Like it's kind of nice that we have this abstraction of ones and zeros, so you never have to think about how they make it work. And the truth is, the only people that worry about even this are the people who make compilers, the people who have to know, well, how do I take JavaScript code and turn it into ones and zeros? Like, how do I turn it into the equivalent of what this processor can actually do? But it really is just this one-to-one thing, and all computers do is add things, subtract things, move things from one place to another. And we have this thing here, which sometimes they shift things. And we'll just show that as like an interesting point about binary and the difference between like how you might do something and how something might be done with a computer. So if I have a number like 1, 1, 0, 1, 1, 2, oh, what? Not a 2. 1, 0. So what does this represent? That's 0, 2, 4, 8, 16, 32, 64. So this is equal to 96, 70, 80? Is that right? Does this mean 80? Did I add it right? Okay, so no, because 6 and 3 is 9. So I clearly got that wrong. 96 plus 4 is 100, 110. Let's just say this equals 110. And sometimes when you're doing something, you'll do like an if statement, and you'll say if like x mod 2 equals 0. So this is pretty common where you're saying if x modulus 2, so when you divide x by 2, does it equal exactly 0? Or does it equal 1? And if it equals exactly 0, then that means that it's an even number. So how might this actually be done by a compiler? First off, I did not learn this even in my CS degree. Someone gave me this in an interview, and I'm like, I cannot believe you're asking me binary, but the people who learned this, like the people who this is what they learned in college, they think it's really important. You need to be able to think of exactly what the compiler is doing. So x mod 2 equals 0. So how might I do that here? Well, this operation could actually be what I'd call a left shift. So left shift 1. Left shift, and the value is 1 of this. Let's say I'll call this $T0. So let's say this was how my let's say this was my instruction. I could say like left shift, because it probably provides me that. Shift only 1 and shift this thing. So I would say take 11, 0, 11, 0, and shift it over by 1, which means push it this way. And what that returns is it just drops whatever the last number is. Sorry, it drops whatever the last number is. So we just shifted it over to get rid of that. And if we add this up, that's 1, 2, 4, 16, 32. And that's 48, 50, 55. And you'll notice this is half of that. And that's just like, that is a bitwise trick that you divide by 2 by shifting it. And that's something you never use unless you have to write the assembly, and then you actually don't have this in your language. But you do have this, and that's enough. And it just happens to be that that is how you actually accomplish that. So compilers and interpreters, you'll hear both of these terms. The difference between a compiler and an interpreter is pretty academic and not really worth distinguishing. And it gets more complicated. So what is a compiler? A compiler takes source code, like let's say JavaScript, and it turns it into ones and zeros. Not directly. There's this in-between thing called object code, because your operating system generally won't give a programming language direct access to everything. And so this is some sort of intermediary that your operating system takes and then turns that into the machine code. But an interpreter is different. An interpreter is this idea of it's a program that runs, and while it runs, you can continue to provide it code, and one line at a time, it turns it into machine code and then runs it. That's how JavaScript actually works. JavaScript has a runtime. So some languages like C, they are compiled. You take your source code, and then you compile it, and it takes a long time, and then what it spits out is a file that if you open it up, it's all ones and zeros that your computer understands, but you don't. JavaScript, you run this program, in this case Node, and when you're running Node, you can provide it your program, and one line at a time, it reads it and executes it. So that's called a JIT, or just-in-time compilation. What it means is that one line at a time, not exactly one line, but like one code block at a time, it's going to turn that into something your computer can execute. The downside to that is it is a lot slower. So you might say, like, why ever use an interpreted language? That is a good question. The good part of a interpreted language is you don't need to know what hardware is running on a person's computer when you're compiling. Essentially, you're not you're not actually running the code until it gets on whatever computer and whatever architecture that computer is on that it needs to translate it to. And that's actually pretty important for the web because when something runs on the front end, that is not your computer. And you have no clue what the architecture of their computer is or what their processor looks like. So there'd be no way of compiling it ahead of time unless you knew every possible computer that wanted to visit your website. And you don't want to do that. So instead, you write your JavaScript code once, you send it to the user, and then Google Chrome is going to take your JavaScript code, and it knows how to read the hardware and say, okay, they have this hardware, so one line at a time, I need to translate it into the instructions that that hardware understands. So this is a general outline of what steps happen. So like I said, I'm not going to really distinguish between compilation and interpretation. Interpretation just means it's going to compile it, but not in one big thing. It's going to compile it one thing at a time. And that's why you get something like a REPL where you can, type one thing and it spits something out. And you type another thing and it spits something out. And you can say var x equals 4, and for the rest of the time you're using the interpreter, that is now true, x equals 4. So you start with your source code, and that's the only thing you care about. And what it outputs, even if you never see it, is this thing called object code. And object code is saying, here are all the files that I want. If I'm importing some code or a library, I found out very late. Have you guys ever used Windows and they have a .dll, and you're like, what is a DLL? Why is stuff not working because I don't have a DLL? A DLL stands for Dynamically Linked Library. And basically, it's a bunch of precompiled code that your code needs to run. And so it's some way of saying, well, we're not going to recompile that code every time, but we're going to put a little marker in your code that says, he wants that, and we've already compiled it, so go grab it from here. That's the kind of stuff that happens at this level. It's your operating system making all these optimizations so that it does as little work as possible. And then your operating system is over here. Your operating system's job is basically to say when some program runs and when some other program runs. So we don't think of it this way, but when you type something on your computer, basically your computer only ever does one thing at a time. The only way that it seems like it's doing a lot of things is because it's switching off. So let's say you're typing something in Word and then you're also playing Spotify. What's actually happening is you type something, the computer listens, it updates the screen. But then it's going to pause that for a second and say, okay, well, you actually are playing this music and it's been more than 3 seconds, so we're going to talk to Spotify, get 3 more seconds of audio, and send it to the speakers. And once that's done, we get back to doing whatever we were doing with you typing into Word. And that's why sometimes you get that beach ball or, things are a little laggy. It's because your computer runs lots and lots of processes at a time. We'll talk about this more later, but if I say activity monitor here, my computer is running how many processes? Well, a bunch. I don't know. I can't count this. But it's a lot of them. And as you'll see, things like Google Chrome are just always spinning up processes in the background, which makes you think, what are they doing? But that's how it works, and we all like using Chrome, so we put up with it. And yeah, you can see here, QuickTime is it's only one process, but it's dominating my CPU. So 25% of the time my CPU is doing something. It's working with QuickTime because that's the most heavy-duty thing my computer is doing right now. And you see there's all this idle time, wake up. There's threads, which means it's that process itself is able to split its work up into a bunch of different things. And let's say I had 15 processors on my computer, which I don't. It could have each one of those things do one of these 15 different threads. In reality, it's only doing 4, but I guess something like QuickTime knows to be really fast if you happen to have a computer that can split up work that much. Okay. Yeah, and your operating system obviously finally talks to your hardware, which only understands machine code. But there are all these levels that you kind of never think about. And it's worth knowing they exist. But for the most part, we stick up here. The real craft of programming is learning how to write in whatever language you write in. And you assume that whoever implemented the compiler for that language did the right job and the documentation matches how it actually works. And if it doesn't, it's not your fault, and someone is going to get fired at Google or Microsoft or the handful of places that make programming languages. So we can safely stay up here, and the truth is there's more than enough up here to occupy you for the rest of your life. And the web is at a point right now where there's actually too much for any one person to know. Like, you can become an expert in CSS, spend your whole life just knowing CSS, and like, that's one path to go down. But that's probably a good thing that, all of this technology has grown to such a degree that no one is writing stuff that works directly on the hardware. Everyone is writing stuff that works on some other layer, on some other layer, on some other layer. And it's really getting rid of something you don't want to have to think about. So the primary stuff that's taken care of for you by this in JavaScript is the fact that when you say var x equals 4, you never had to say, OK, computer, I want to put a 4 somewhere and be able to refer to it later. So how much space does a 4 take up? Well, it takes up 32 bits on my computer, let's say. OK, so I need 32 bits. Can you find some 32 bits for me? It finds some. And then it says, here's the address of that 32 bits. But when you're done with it, you have to tell me you're done with it. Otherwise, a future program that wants it can't use it. And that is what you do in a language like C. So you're not going to use it in this course, but this is what C looks like. And you have this, which is called a pointer or a dereference, and this, which is an address. And so in here, we're saying, OK, we're creating a character, and then I want you to grab the address of that character. So that character lives somewhere in memory, and let's say its memory address is like 10,000. It's just like your street address. It's a unique address that the computer can jump to immediately and read whatever's there. And it knows that when you say, I want to go to this address, you're talking about that specific place. And so what we're saying here is, OK, so we have a pointer, which instead of holding a value like C, it actually is going to hold a number, which is the address where this lives in memory. And then here I'm saying, OK, T, which is a character, I want you to take whatever is in this location in memory and dereference it. So get me what's actually at that location in memory. If that's a little confusing, I will tell you that pointers are the breaking point for most people who are doing a CS degree. It's like this very weird low-level thing you have to learn a language like C. But by and large, the only reason you do C anymore is if you're doing video games or something else that requires just maximum efficiency from your computer, or if you're doing something like, let's say you're making a microwave or something. You might want this microwave to run on a tiny little chip, and you want it to use as little electricity as possible. And so you'll probably use C because you don't have to think in these high-level abstractions, and your big concern is like saving power. But that's really the reason to do this stuff yourself, that you can be as efficient as possible if you know what you're doing. A fun thing, the guy who made the game Roller Coaster Tycoon is incredible at assembly, and he built that game in assembly. I once had an assignment where we had to essentially put colors on a screen and then scroll them in assembly. That took like 40 hours, and I didn't do it. I have no clue how you make a video game in assembly. It's such a low level to think about everything, but it can be done. But similarly to this, JavaScript is what's called a garbage collected language. So most languages these days are garbage collected, and what that means is that you never have to think about specific pieces of memory. JavaScript's going to handle that for you, and it's also going to keep track of what variables you're using and what variables you're not using, and anything you're not using anymore, it will garbage collect. So let's say you have a function, and that function takes two variables. Well, when that function is run, it needs to create those two variables, but when that function's done, it doesn't need them anymore. And the idea is the garbage collector pays attention to that and gets rid of them when it doesn't need it. In C, you essentially have to do all of that bookkeeping yourself, and that is where the blue screen of death comes from in Windows. That's called a segmentation fault, and it's basically the compiler is smart enough to know you shouldn't be accessing this memory, but the language allows you to. And that's also where 90% of various hacking things happen. because C is this language that says we're as efficient as possible, so we actually don't put up guardrails, and you have to be very careful if someone's going to overwrite some memory you don't want them to overwrite, because a lot of times if you're not checking, if you say like, oh, type in your username, and they expect your username to only be like at most 100 characters, and instead you type in this massive script, it will actually write, if you're not checking and you're doing it in C, it will write that in the memory of their computer, and now they have a program sitting on their computer that they didn't want in there just because you weren't checking that they didn't use like that username wasn't much bigger. That's what, it's related to that Heartbleed bug. Do you remember that a bunch of years ago? The Heartbleed bug was this thing where some open source software that people use for SSH, which is Secure Shell Handler, was not so secure. And the reason it was not so secure, which is something worth paying attention to, and this is why whenever I write an if statement, I always write it with the braces, even if I'm only going to do one line or something. Because let's say I wrote it like this, you might know that if I say like if true var x equals 1, and then I'll say var y equals 2. Maybe I wanted it to be that I only do these two things if this thing is true. But because I didn't use the braces, it actually only applied to this, and then this statement is always executed. And that's what the Heartbleed bug was. It was literally someone forgot to use braces, and something that should have only happened if someone was like authenticated happened no matter what. And it let people overwrite things and do all this terrible stuff that I don't really understand, but I guarantee you someone at Apple, if they didn't get fired over it, they got reprimanded. Although, in my experience, the sad reality of big software companies is testing is the last thing they care about also. They'd rather get it out the door and fix the bugs later. But for certain things like banking or anything where like money or identity is involved, people get very intense about security, and that is just one more reason why it's kind of nice to not have to worry about memory yourself. All right, part 4, abstract data types and data structures. So we're going to be talking a fair amount about this right now. Something that's kind of hard to talk about with data structures in JavaScript is that so when we talk about an array in JavaScript, it can be either of these things. So let's think of memory as this here it looks like 2 dimensions, but let's just think of it as a one-dimensional array of values. So the way we want to think about memory is it's just like these boxes. So it's lots and lots of boxes that are in order. And I'm only going to draw so many, but as you can imagine, there's lots and lots of them. And I want to give each one an address because it does have an address. So people often use hexadecimal for this, and to represent that, I'll put in OX in the beginning. But it could just as well be decimal. It's just numbers. So this is 0, 1, 2, 3, 4, 5, 6. And if I'm in a language like C, if I say, so in JavaScript, you can do something like, you make an array. So I'll say like var array equals, 1, 2, 3. And that, if I check the length of this, it's 3, right? But then I can say something like R10 equals 4. And then what this actually looks like is suddenly its length is 11, and it has a bunch of empty things, but the idea is I just grew the length of the array. So in a language like C, you actually can't do that. JavaScript arrays are a pretty high-level thing that kind of wraps over this concept. You don't need to think about it. But if I'm in C, I would say something like, let's say integer array named array is equal to, I might say 1, 2, 3, but forevermore the size of this array is 3. I can remove things from it, but I can't simply add to it. If I want to add to it, I need to create a new array. And the reason is this. When I create an array, what's actually happening is what's going to be returned to here is not a value, but a reference. And that reference might be the reference to 0. So basically, I'm saying that array is a variable that points to here. And then in here, we have 1, 2, 3. So it's contiguous in memory. And the only reason why that works is because everything I'm adding is the exact same length. So I can, like, when I say array 1, I'm saying, OK, well, how big is an integer? It's 32 bits. So I want to skip 32 bits. And now whatever address I'm at, this plus 32 bits, I'm at the address of my second thing. And that's what an actual array looks like. It can't grow, but it's really useful for randomly accessing things because you can just jump to it. So what is this thing called a linked list? So a linked list is similar, but it doesn't give you the random access. The positive to it is that you don't need to know the size of your thing when you start. So in a linked list, what I'm doing is, so when we have those 4 things, we're sort of like creating a certain amount of data where I'm going to hold a reference in my last thing to whatever I care about. So let's say I have 1, 2, 3, but then I want to know, but then like I want to continue my list in another part of memory because, you know, asking for 4 or 10 blocks of memory isn't that much, but let's say you're trying to save a DVD. Chances are your computer doesn't have like 4 billion blocks sitting in a row. And if you've ever defragmented a hard drive, that's exactly what you're doing. You're telling it to reorganize the bits so you have a bunch of free stuff in a row because that's useful for certain things. But what I might have here is like 1, 2, 3, and then like 0x5. And what this means is go to 1, go to 2, go to 3, and then once I'm here, well, actually, it continues somewhere else. 4, 5. And you can just keep doing that. And the idea there is that now I don't need to have it as one big block. I can break it up, but I broke it up by having these references. The big downside to that is I no longer have this instant access thing. So before, whereas I could say like array 4, and I knew to start here and just add 4. Is that right, or should I say 3? I'm not counting right. Well, I can't do that anymore in this case, because in this case, my 4th element is not here. Instead, there's a reference here. My 4th element happens to be here, but there's no way starting from here to know it's there. Instead, I have to walk one item at a time and say, OK, now I found the reference. I can go to the next thing. So you see there's a fundamental trade-off there. When we're dealing with contiguous arrays, and when we say array as a data structure, that's really what we're talking about. It gets a little confusing because JavaScript arrays are, you know, they break all the rules of arrays. It's actually behind the scenes, it's doing one or the other of this depending on what's most efficient at that time. So that's the nature of a high-level language that, like, they're thinking about this problem for you. You never have to think about it. But we're still going to be implementing some version of it today. Right, so the benefit of an array is that if I want to access the 55th element, I just jump to the 55th element. But the downside is it all has to live in memory, one next to the other. The benefit of a linked list is that I can break it up as much as possible. But the downside is that if I want to access the 55th element, I have to walk through the first 54 elements. And that's kind of the same thing as that book and scroll thing we were talking about earlier. So a scroll is like this, where if I want to get to the 55th page, I actually have to walk through each one. I mean, this isn't quite the same because this is almost like a tiny little scroll that at the end of the scroll says, see the next scroll. But the book is the contiguous one, where it's one big thing, but because it's all right next to each other, I can take the shortcut of like jumping to whatever index of it that I want. So this is how something might look behind the scenes in a language like C. So in this case, I'm saying I have this variable vals, and because it's C, you have to provide the type, and it can only have one type. And I'm saying it's going to store integers that are 8 bits long. And its length is only 5. So what that is going to return to me is some address in memory over here, and this is everything that's been given to me. And vals holds this memory address, which happens to be 3A6 over here. And then when I say val0 equals 9, what's happening is that I take this memory address and I say I want to index it by 0. So I take that memory address and I add 0 times 8 bits. So just 0. So I stay at that exact memory address, and then I place a 9 wherever that is. And now a 9 lives there. Same thing here. So I have a 3. So what I say here is, okay, I want to index it by 3. So I know that each, we're dealing with bytes here, so each one is a byte. So I want to jump 3 bytes ahead from whatever the location of vals is. So I start at 0x3A6. I add 3. It's simple because it's just a byte. So like, you know, it would be different if like each one was 2 bytes or something, but it's just a byte. So we're at this address, which is right here, and that's where we place something. And similarly, when we try and grab something, we're grabbing something from that memory address. We're jumping 2 ahead, and then we're trying to get whatever's there. So that's how an array actually looks underneath the hood. So an array is an example of a data structure, as is a linked list. These are data structures, meaning they're ways of providing your data with meaning. So like when you move from left to right, everything is just ones and zeros. But depending on how you want to read that data, it makes a difference. So even though I'm still representing my linked list in terms of a physical array in memory, because that's all there is in memory. There's just this, you can think of it as just being this one really long string of memory addresses. The fact is, I know how to read it, so I know that this is not a value here. I know that, you know, I probably have some way of representing that I don't want to treat this like a value. I want to treat this like an address. So when I get here, I know that this isn't what I want to look at. I actually want to jump to here and return this value. So arrays and linked lists are examples of data structures in that they give your data meaning directly. And we'll see more of that with like trees. So you can represent any number of things in memory, and like a tree is a way of organizing your data where there's like branches. You can have what's on the left or what's on the right. But then there's also this thing called an abstract data type. And what makes an abstract data type interesting is that it has nothing to do with the data structure that it is implemented on. So you can use any data structure to implement a given abstract data type. All that an abstract data type is a definition of what sort of operations it needs to be able to do and like what we expect those operations to return. So in this case, for a stack is something that you can push something on top of it. You can pop something off of the top. Oftentimes, you can check what's at the top element and or check if it's empty. And I guess the ability to clear everything off of it. But the primary thing here is push and pop. And a stack does last in, first out. So do you remember that game Towers of Hanoi? You probably don't know that it's called that, but it's like you have these like 3 things, one smaller than the other, and it's like you can't move the big one until you move everything that's on top of it. So a stack is similar to that. It's this idea that whoever was the last one to be put in the list is at the very top, so they're the first one to be added. They're the first one to be taken off if you pop. So what we would think of here is like we keep pushing pancakes, and then this last pancake gets pushed at the very top, and then if we want to pop from this stack of pancakes, we don't take the pancake on the bottom, we take the pancake on the top. And a stack is an abstract data type that says, I don't care how you implement this. It's an array, it's a linked list. All I care about is that it's easy for me to put something at the top, and it's easy for me to take something off the top. And it satisfies this rule. Whatever was the last one that I put in is what I want to come out first. surprised. I think we do queues a little later. But a queue is a very similar idea, but instead of last in, first out, it's first in, first out. And a queue is kind of trivial to think about. Why don't we get some volunteers? Can we get 3 people to stand up and come to the front? The enthusiasm is palpable. 1 more, or else we're shutting Grace Hopper down. All right. Okay, great. Very brave. All right, so let's say I'm selling donuts and you guys want donuts. What do we in a polite society do in order to get donuts? We line up, right? And it would be pretty unfair if I'm like, okay, last in gets the first donut. You could do that. That is a stack, but that's not terribly fair. I do want to think of an example of where a stack makes sense. It's used in places, and a lot of the stuff is used lower than what you, like you'll rarely make these yourself when you're programming day to day, but like the data structures you do use do have these under the hood. So exactly, right, first in, first out is like, okay, so if you guys are lined up as person 1, person 2, and person 3, if I say DQ, so if I say get the next thing, that's you. And then I give it to you, and then you're gone. And then I say DQ. And you're gone. I gave you something. And then if I said NQ, if I said I want to add something, does the person I add go in front or behind? Behind, exactly, because it's a line. First in, first out. Whereas if it was a stack, they come here and then they get it, and the idea is being first is terrible if you're in a stack. You're going to be served absolutely last. So I give you the donut or whatever I'm giving out. This is improv. And then, cool. We don't have actual donuts. Maybe one day we'll have food. So yeah, there's lots of abstract data types. This is just saying like how you would implement it with an array. So let's say we're trying to implement each one of these features of a stack within an array. So collection of elements, well, we have an array, so that's pretty obvious. If we have just going to check the time quickly. We're doing okay. All right, so I have an array here, and I'm trying to make a stack. Okay, so it's ordered. Yeah, it's already ordered, so I don't really have to worry about that. How do I create a new stack? Well, I'm just going to make one of these. So my stack is an array. And then how would I push something onto the stack? So I'm saying I want to push 1 onto this stack. Where should it go? Yeah, so I need to make like some sort of top variable. And where does it make sense to put the top? I guess it doesn't really matter. I'll put it at the first thing. But I'll just say, OK, top points here, and I put a 1 in there. And now I want to push another thing. OK, so what do I do now that I pushed another thing? Sure.
Push it on top so that 1 has to go towards the bottom, and then the 1 is now the bottom, and then your new thing is the top.
Yeah, so one way I could do it is I push this 1 over here, and now I have a 2 here. But that actually gets pretty expensive if I'm pushing things over all the time. So instead, I could just put my 2 right here, but I say, OK, top is actually whatever the most recent thing was. And I know to look here. And now I say pop. So pop, I don't need to give it an argument. I just say pop. So when I pop, what is it that I want to return? 2, yeah, whatever's currently at the top. So I return 2, it disappears, and now I need to find my most recent top, and that will be whatever the previous thing I added was. So now we go back here, and now how do I know if it's empty? Well, to see that it's empty, I check whether the array has anything in it. Maybe I check if top points to anything. If it points to nothing, I'll say, OK, well, it's empty, but if it points to something, it's not empty. And so in this case, an array was our data structure, but stack was our abstract data type. We happen to represent it as an array, but we could have just as well represented it as a linked list. So let's do that, actually. Let's try and represent the same exact thing as a linked list. OK, so we're going to try and make a stack and do the same thing. So when I create a new stack, I'm going to create a linked list. And I like to represent that like this. So we're going to have the value in here. And we're going to have some sort of pointer here. And where the memory address it points to will generally go like that to say, like, oh, it points to this other piece of memory. And on until it points to nothing. And that is what null is good for. Null is to say, well, we're done pointing at stuff. OK, so when I say push, let's say I'm starting with this thing called top. Top has nothing in it. So what do I want to do with top? When I push 1 and I see that top is null right now. Yes, so I want to say, OK, so top is actually pointing to this new thing I'm creating. That new thing is going to have a 1 in it, and it points to nothing. And now I want to push 2. So what do we want to do now? So you're saying make 2, and then point, so this goes to nothing, and then this actually now goes here. Let me draw it more like, OK, so I had 1 here, and 2, and nothing. But what happens to top? Yeah, at that point, I can put top here. And that is an approach, but let's say I pop it now. So what do I want to do when I pop something? I want to get rid of what's at top, right? So I'm going to return 2. So I return 2, and then I destroy this. But actually, how do I know where do I want to reassign top to? But consider that I only had access to this. I only had access to this, so how do I maintain access to what I actually want? Yeah, that's fair. Like I can point it here, but well, the idea is I'm pointing it at this whole thing. The problem is that like I want to know to immediately pop this, otherwise I'll walk to the end, right? So even though we're implementing it as a linked list, it still matters sort of how we decide to connect things. So the way I would actually do it is more like this. So we start with our 1, and that goes nowhere, and then we make a 2. Sorry, I'm going to make my 2 over here. But actually, my 2 is the new top. And what I want my 2 to do is my 2 has a next. That's generally what we call this pointer. It's like where it goes next. And that next, I want to go to this. So that when I decide to pop something, I'm going to pop what's off the top. So I say, OK, return 2. But before I get rid of it, the new top should be whatever was after 2. So top.next, so top equals top.next. And I do that, and now this is my new top. And let's say I pop again. I'll return 1. And because the next of that was null, it points to nothing. And so we just implemented a stack, but in 2 different ways. And as you saw, like there was another way to do this. It just wouldn't be as efficient. So that's a big part of what makes an abstract data type matter. We're not going to get into that too much today, but there's this idea of complexity analysis, which says like, how long does it take to do something? And when it comes to an array or a linked list, the worst case is I have to walk through every other element before I can do that. And the way we were doing it with the pointers initially, that was perfectly fine. It would have worked, but we would have had to walk through if I wanted to see the thing I wanted to pop, well, I was starting at the top, and I'd have to walk through every single element until I got to the last one. And because we just did it a slightly different way, now that becomes a constant time operation. It's always the first element. And that's nice because it means it takes less time. So what we have here are a bunch of different data types. Some of these even exist in JavaScript directly now because of ES6. We have a map, which is in JavaScript now. I don't know if we explicitly have, oh, we have sets. Sets are an explicit thing. Really, this list is very big, and you're not even going to need to know a quarter of this stuff when it comes to interviewing. Like, I could not tell you what a red-black tree is at this point. I know that someone mentioned it once. If someone asks you about a red-black tree on an interview, I genuinely believe you should get up and say, who do you think you are? You tell me what a red-black tree is. Literally, when was the last time you used that? And if they have an answer, then that was bad advice. But I like, unless you're building operating systems or like caring about like really low level, how do we make sure that the memory hierarchy has what you want? You don't touch a great deal of this stuff. So what about JavaScript? JavaScript has some built-in types, and you're going to use these built-in types a lot because they're built in. In fact, you're probably going to be saying to us at the end of this workshop, why did you make us do this? We're never going to use this. And it's like, yeah, because the array in JavaScript has the best qualities of both a standard array and a linked list. It just makes it so you don't have to think about it, and you have all the positive qualities, and just get on with your life, do whatever you want it to do with this array. So built-in types in a language are the language telling you essentially how it thinks you should do things. It's saying, we spend all this time to provide these data structures out of the box, so why not use them? So only have a few minutes left here, but who can tell me what the data just let's try and name some data types that are in JavaScript, because there's only so many. So what are the data types? Like, what types of data exist? Numbers, very good. What was that, strings? Arrays and objects will count as one thing. What was that? Yeah, in JavaScript, interestingly enough, many things are ultimately just objects. So at this point, functions are objects. Everything is objects. But as it turns out, undefined and null also count as their own types. They're unique types in that they're the only thing in that type. Undefined is generally, the idea is try and only use it when it comes to something that just hasn't been assigned yet. It shouldn't have a meaning yet. It's rare, but when you say something like var x, and you don't say var x equals 1, you just say var x. I'm saying something x exists, but I've never defined what it should be. Whereas null is a way of saying, here's an object that represents the no object. So just like 0 represents the no number, null represents the object that is just the null object. And we have Boolean, which is true or false, pretty important type. And then finally, there's this thing in ES6 now called symbols. I thought I knew what it was because other languages have something called symbols. I have no clue exactly what JavaScript symbols are. I've tried to figure out where you would use them, but you can read about it. You can read about the documentation. You'll probably not encounter it until you're like doing something very fancy, but I know that it's used in the language in some ways. I think the idea of a symbol is that two symbols are never alike. So if I make a symbol, so if I have a string A and a string lowercase a, if I compare them, they're identical. Whereas if I have a symbol lowercase a and another symbol lowercase a, every symbol is fundamentally unique. So it's a way of giving something an identifier that is guaranteed to be unique from any other identifier in the language. And that's useful at times, I guess. Like I said, I have yet to find a reason to use it. So these are our primitive data types, but then we also have non-primitive data types. And that means that we have types that are really collections in some fashion of other types. And the most common one, by far, is an object. And an object is what we call a map. An object lets you say, there's something on the left, and I want you to associate it with something on the right. So if I have an object in JavaScript, it has, I mean, there's a million things. There's lots of names you can give this stuff. I like to say it is a field, and then the field has a value. Some people say key value pairs. But the idea is I have a key, and it holds a value. So when I say, so if this is my object, if I want to get what's at that key, I say object.key or object key. And it could actually be anything. It could be a number. And that's actually how arrays are done in JavaScript. It's literally just an object that has this thing called length on it, and that has keys that are 0, 1, 2, 3, etc. I could even have a Boolean there. Well, this is probably going to treat it like a string, so maybe not going to do that. On the left, you usually do have a string. And this is called a map. We're actually, in the second part of the data structures workshop, you build what's called a hash table, and that is what this is. It's kind of complicated to implement yourself, but luckily, at the end of data structures part 2, you won't do it, and when you're done with that, you'll say, why did we even do this? Why didn't we use an object? Because if you used an object, it would be trivial because they already did it for you. We are going to try and make you do it in some other way, and then you'll be thankful that someone built a language for you, because as you can see, programming computers without the help of many, many people who've done all the other work would be really, really frustrating. So we're about done here. We're about 2 minutes over, but I really think the pass by value, pass by reference thing is like so important. And when we're talking about memory is the perfect time to talk about it, because it is a language feature that you kind of have to understand what's happening behind the scenes to know why they're doing what they're doing. So if I have some JavaScript, let's say this is going to be my JavaScript, and I'm going to have a function which I'm going to, my function is going to be called add x. Now I'll make this an arbitrary function that I'm just going to call f. And it's going to take an x, and it's going to say return x plus 1. So this is like some simple function that just adds 1 to whatever I pass it. And then I'm going to say something like var n equals 1, and then var m equals f of n. And you see how this can be very mathy, or can look like math if you wanted to. So all of your primitive things, your numbers, your booleans, your strings, are what's called pass by value. So if I say let x equals 5, behind the scenes I'm saying there's this value, there's this identifier x, and it equals 5. And then I say let y equals x. So what do I think y is going to equal when this line executes? It's going to be equal to 5. But an important thing to note here, it's not the same 5. So if I now say x equals 8, this updates, but if I try and print y, it's still 5. And you'll see that this is true. And what is the reason for this? The reason for this, well, first, pass by value is considered the basic way of doing things, and it's safe. It's safe because if you pass something to a function that's passed by value, the function can't modify it from out under you. So let's say in this function here, I just said x plus 1. So here's what's going to happen. I created this function that lives somewhere, and then I have all of my memory here. And I have something called n, and in n I have a 1. And then I'm trying to make this thing m, but first I call this function. So I say f of n. And that actually will make a new variable called x, and it will put a 1 in it. And then for this new variable, let's say I'm saying x, I'm going to say x plus equals 1. Plus equals 1. So that is going to turn this into a 2. But you know what? What am I doing here? I'm just going to return this. So I'm going to return x. So I return x, and that's going to return here. So I have this m that is equal to 2. But if I look at n didn't change. Because when I called this function, I took what was in n, but I copied it over to a brand new value, in this case called x, and that's what I did all my work on. There's no way by passing n in as an argument that I could ever change what n equals. And that's a pretty important, useful guarantee, that passing something in as a parameter can never change what was originally held in that parameter. It's sort of like it's read-only. You're able to read what was in that parameter, but you can't, you're able to read what was in that variable, but there's no way that what that variable holds can be changed out from under you. And that is true of all of your primitives. It's true of strings and all these sorts of things. You're always making a copy whenever you call a function. But composite types are different. So your non-primitive types, particularly objects, are different. Hey, how we doing? All right, cool. Yeah, we're wrapping up. We're wrapping up. Right, so how does pass by reference work? So here's an object. Let x equals age 5. So I'm saying x now refers to this object, age 5. And I say let y equals x. So what do we think is going to happen here? It's one of two possible things. Either y will hold a brand new object, or y will be another variable, but it points to the exact same object. Exactly. So this time we're doing reference. It actually is just another variable that points to that same thing. What that means, if I say x.age equals 8, well, I change what that holds, what x holds onto. And now when I check y, well, y does not have its own unique copy. So whatever change applied to x also applies to y, because they're just looking at the same object. And what does that look like in memory? So I'm simplifying when I do this stuff in memory where I'm putting all of it in one memory block. In reality, things take up more than one memory block, but okay, so let's say here I do something like x.age equals 4. And so I'll say n is equal to an object, and that object has age in it of 4. And then I call this function on it. So what happens? So first in n, I have an object, age 4. And for the purposes of this, I'm actually going to also say even though I have these indicators of what I care about, I'm going to also say these are memory addresses. Okay, so this has this object in here. And then I call the function on n. So what actually gets put in x is not a brand new copy. Instead, it's just this. It's just a reference to the actual thing we want. So when I'm at x, I say, OK, I have 0x1, and I want to access the age property of it. So because it's a reference, I jump here. I take that age. Well, let's assume this was originally 1. OK, so I'm overwriting what is at the age thing. Now it's a 4. And my function's done. So first, m didn't return anything. So that's silly. M is just going to be undefined, I believe. And actually, whenever a function, if I have a function that has a parameter, when that function's done running, anything it created also disappears. But if I were now to check what n.age was, this is not true anymore, because by passing it into this function, it's possible it changes something about it out from under me, and that's exactly what it did. And the truth is, that is the source of the great majority of bugs, which is why not everyone believes you should pass things by reference. And way, way later in the course, we're going to talk about this thing called functional programming, which is this idea that everything should be passed by value, everything should be copied. You should never allow it to be possible that by passing something into a function, things could actually be changed. But that is exactly what is possible. And we are done for now. OK, so Gabby, it seems like you got something to say.